Okay, maybe it's time to start. But before starting the lecture, I have one announcement or one comment. Actually, I made an error in the one previous class or many previous classes, and I just fixed that. Okay, I delivered some misinformation. It's about the Bode plot sketch, asymptotic plot. Suppose we have this kind of transfer function. Transfer function is this one. S divided by, let me move this, no. Let me move this guy to, okay. Right. So S divided by 1 plus S divided by Q omega naught plus S squared divided by omega naught squared. Okay. And another one is this one. This is the simple second order low pass filter with single quadratic term in the denominator. Okay. So this one start from the differentiation. So it will start plus 1 slope, and the slope will be lowered by 2, so it becomes like that. So this is a plus 1 slope, and this is minus slope, and this is the resonant frequency. Downward frequency omega naught, and there is a peaking, something like this. Thing is, this one is symmetric. Then the phase evaluate at this peak is 0. Okay, I think I said whenever you see this, assume phase at this frequency is 0. That is not true. That is true when this asymptotic plot is symmetrical with respect to this axis. But if that is not true, then the phase at the peak is not 0. Suppose this one is this transfer function. Then it starts from the 0 dB, and it goes up and has some peaking like that. And this is minus 2 slope, 0 slope. And phase of this frequencies, this one is 0, this one is minus 180, and the phase this point is minus 90, not 0. 0 is here. Okay? So just seeing this peak does not guarantee the 0 degree of phase. Okay? If everything is symmetric, then makes sense. I thought when this is on the top of here, the phase is 0, but that is not true. Okay? Maybe we need some length, okay, range of the frequency to sit on this top. So this one is not 0, but this one is a symmetrical one 0. But if this 0 is staying for a while, like it has some line segment, and it has some line segment like this, then phase here is 0. So we need some length to assume phase during that period, that frequency to be 0. Okay? So that was misinformation. Okay, so I fixed this, right? Okay. Now we start a new section, and the section title is Frequency Response of PWM Converter. So this is a new section, and this is the beginning of the real dynamic analysis of PWM Converter. So previous one it was some basic background based on the linear time invariant system. Now we are focusing on the PWM converters, which is non-linear and the time varying system. And in particular, we focus how to extend the idea of the linear time invariant system, particularly the frequency response, to this non-linear time varying PWM converters. What are the benefits of doing that, and what is the implication of doing that, and what is the limitation resulting from the non-linearity and the time variance of PWM converter. All of them are discussed. Okay. Somehow we want to the same story, the same as the linear time invariant system, or similar to the invariant linear time invariant system will be true in this system, but that is not the case. But mostly they are very similar. So understanding the basic background of linear time invariant system is critical to understand the nonlinear dynamics of PWM converter. So I prepared 2 slides to demonstrate the concept of frequency response in PWM converter. Here is a situation. This is a buck converter, and this is input. This is the DC originally, but we added some AC component. So input voltage is not DC anymore. It has large DC and the small AC component. Okay, so this is the situation. Then what you are expecting is this out voltage. If that was the purely DC, and this the duty ratio of this switch drive signal is fixed, periodic. Okay, it is periodic with the constant this. It is a periodic. Okay, that is assumption. But input voltage has some DC value, and on top of that, it has some AC component. That what you are expecting is the out voltage. Without this, with the periodic this switch drive signal, our voltage will be constant dVs, and there is some ripple component at the switching frequency. Okay, that is the that is the true. But if you add some sinusoidal component here, relatively small means compared to the DC value, this AC component is small, then the out voltage will be something like this. It has the average value, DC value, which is identical to dBs, and it has this sinusoidal component originated from this one, and it also has some ripple component on this. Okay, so this is our expectation. Then, if you consider this sinusoidal AC is input, and this value, you take out the ripple component and take out DC component, then you may think AC in, AC out. Then you may think there is some frequency response of this converter at particular frequency. Okay, that is the basic concept here. And to show that, I did some simulation. This is a switch drive signal. When this QT is 1, switch is turned on. When QC is 0, then switch is turned off. This is a periodic with identical duty ratio for each and every switching period. So this is constant. But this input voltage, the average value was DC. This is our previous assumption. But on the top of that, you have some sinusoidal component. Then our voltage will be like this. Okay, without this AC component in the Vs, the out voltage will be this DC value, and the switching ripple is on it, something like this. Okay, something like this. But with this sinusoidal variation, there is just some sinusoidal component at this frequency. Okay, so you may want to relate this one and this sinusoidal component. So when average is taken, this, so you want to relate this one and this one using the concept of sinusoidal component, and you strip this evaluation frequency, that will be the frequency response of this converter. Okay, so concept is very similar to the LTI system, but we are just forgetting this DC component and this ripple component. That is the basic idea. But one critical things to note here is we are comparing, this is the AC waveforms and this is the AC waveforms, but this is this is the analog waveforms, AC and analog waveforms, and this is also analog waveforms, DC plus AC, but this one is something else. This is a pulse waveform. So when we are comparing two waveforms, we want to compare the apple with apple. We don't want to compare apple with orange. All right. So we need to find something from this, some continuous signal. That concept is shown here. Okay. So dt is continuous duty ratio. So we averaged this value, and averaging period is Ts. Okay. So this quantity, we integrate this one. This is this switch function which varies between 1 and 0, and we integrated that and we divide by this switching period. That is called continuous duty ratio, and this is moving average of switching function Qt. Okay. Because this is the switching function. It has number 1 and 0, and this will be a number. Right? So this is, we are averaged, but averaging period is Ts. Okay? Moving average of switching function Qt over, we take this operation over the switching period. If this is a periodic, this is a constant. This integration and divided by Ts is a constant. Right? Why is that? It does not depend on value of duty ratio. If this is the periodic, it becomes constant. Okay? Think about this. This is the switch drive signal waveforms, something like this, and this duty ratio is fixed. So when duty ratio, the integration is performed for this period, and this value is 0, then integration is 1, and divided by this period would be 0.5. So D here is 0.5, right? And you are sliding this period, integration period, averaging period. So you slide this, you are moving this direction, then this part is gone. This part is gone, but this is coming in. Then average, oh no, right. So, okay, let me draw this way. For this situation, you are integrating this plus this. Okay? So we lost this much, but we gained this much. So the integration and divided by Ts will remain the same. And if this is the further slide in right direction, then this will be the same. So D, all of the D is 0.5. Okay, let me clarify this. Okay, you understand this, right? So periodic means this dt is fixed. This is some imaginary or conceptual variable, but this is also analog signal. So now we are comparing this analog signal with analog signal with analog signal. Okay, so there is no comparability problem. So this is a very important concept, and this quantity is called continuous duty ratio. Okay. Very critical concept of this. The other case, some other case is this one. For this case, this Vs is fixed at this value, so this is constant, but this duty ratio is changing. If you take a close look at this, duty ratio here is large, and the duty ratio is smaller compared to this, and this is large, and this area is smaller, and variation of this is sinusoidally varying. I generate this waveform using some program, simple program, and duty ratio is changing this way. Okay, then this value is now changing. VST remain the same, but still you have this kind of waveforms for the same reason as the previous case. Okay. So we have two different cases. So from here, for this case, Vs is DC plus AC, and this AC is sinusoidal waveform of amplitude Vs at the frequency of omega s. And then VO is, it contains some DC, and this one, hopefully though at the same frequency as this one. Okay, this is true. Okay, and so it has this and this ripple component. We ignore this. When analyze this, we ignore this, and we ignore this term. The remaining term is this, and the output is this one, and the input was this one. Okay, this is the variation of sinusoidal variation of input voltage, and the magnitude of this sinusoidal variation is very small compared to this DC value. That is the assumption, fundamental assumption, and this is called small signal assumption. Okay, something is much smaller than the other one, and the something is AC component, the other one is DC component. Okay, so this is this small signal assumption. Then you compare this, and the ratio between magnitude of these two sinusoidal waveforms is gain response at this particular frequency, which is this. And the phase difference, phase of this thing is 0, and phase of our voltage, AC component of our voltage is set as, then difference is phase response of this converter at particular frequency. Okay? So we expanded the concept of frequency response to the nonlinear time varying PWM converter in this manner. Okay? So I can say same thing here. D is, this is the steady state, this is the average value of this. Now here D is changing. Okay? Previously with periodic switch drive signal dt was constant, but it's changing. Okay? The way it changes is this sinusoidal waveform. So this can be considered as the disturbance in the duty ratio, sinusoidal disturbance, and this is fixed. Okay? If two things varies together, will get mixed up. Okay? One thing is fixed, and the other one is changing in sinusoidal fashion. Okay? Then we have this, and this is also, it has some average value, it has ripple component, but it has also this DC value, and it has some this sinusoidal component, and we want to compare this and this. Okay, the concept is here. D is varying. This is the constant, and the D hat is the hat you are wearing, right? So you are putting on your head. This is a hat. So D hat omega dtt. Then our voltage will be DC plus ripple component, and we ignore all of them. And this is the AC component, sinusoidal component, at the same frequency with different magnitude and phase delay. And this continuous duty ratio is very critical in here. You are modulating this duty ratio to get this and this gain response and the phase response. Okay? This is the conceptual formulation, and somehow we want to visualize this thing experimentally using some hardware. Okay, there are many ways of doing that, and this is the one typical example. So here we have this structure. This is power stage of any PWM converter. We are talking about buck converter, but there are boost converter, there are buck boost converter. There are many variations and numerous variations of 3 basic converters, and any of them can sit here. Okay, this power stage, and this is the load resistor, and this is what? This is a unique gain buffer, and this is a PWM block. Okay, so this is the open loop. Output is cut here, and this is the fixed DC voltage. Suppose this is the R1 and R2. Then VDC is just voltage division R1 plus R2. In the denominator, R2 in numerator is V bias, VDC, I'm sorry. We call it VDC. All right. So this is a VDC. Then this is a unique gain buffer. So the input is virtually same at two terminals. It goes to the output. So this VDC appears here. So Vcon, control voltage here, is actually VDC, which is the fixed value. Then we are comparing this voltage with the Vlamp here. So Vcon is VDC, and fixed duty ratio will be generated. So this is open loop operation with constant frequency. Nothing is changing. Okay, it changes in periodically. There is no sinusoidal component here. This is constant. Output is constant. Then how to introduce some disturbance AC signal here? How to do that? The way doing this is there will be many ways, but one typical way is this. Okay, so without this and this is the same as the previous case, but in here we have this capacitor and this sinusoidal wave. This is high frequency. So at high frequency, at this relatively large capacitor, which is 0.1 microfarad, something like that, then at that frequency, this is shorted. DC is open, then this voltage is VDC. We calculate in the previous lecture slide, plus this one, okay? So VDC plus VP is going through this, and it is a unique gain buffer. Then it becomes Vcon and Vcon star, Vcon hat. Actually, this is VDC, and this one is VP. Star, no, hat. In Korean, sakat, hat. Okay. So this is the small AC signal. It is AC signal, and the amplitude of this is much smaller than this DC value. There is the small signal assumption. Then this control voltage is sum of this. So there is a DC component, and this AC component is sitting on top of the DC component. Then PWM will occur in this manner. So duty ratio will be changed cycle by cycle in some fashion. Okay, I have shown that here with this green curve. Okay, and if you take the continuous duty ratio averaging process explained in the previous slide here, then you will get this sinusoidal component. This red curve is sinusoidal component, and this black line is DC component, and this is the actual cycle by cycle switch drive signal. This is the average version of it, D hat and D hat. Okay, this is the function of this is maybe this is called duty ratio modulation. Modulating means changing something. You change the duty ratio in this fashion, D plus some AC component. So this is doing the duty ratio modulation, and this part is maybe called AC disturbance injection without perturbing this DC bias point. Okay, one of our assumption is everything is talking about. We are talking about everything has the same bias point. Okay, at the fixed bias point, this will happen. Then this will go into this. Then output will be like this DC component, and this sinusoidal component, and the ripple component. And you may consider this is the input to this converter. This is output to this converter, and the transfer function between this and this. Okay, so this is the VP hat is the same as this Vcon hat. So Vcon hat divided by VP hat is 1, right? They are same thing because this is the unit gain buffer. It's the same thing. And Vcon to this duty ratio is something new. It's called modulator gain. Okay. Later on, we derive this, and this value is given by just magnitude of this ramp function in the denominator, and the numerator is just 1. Okay. If this peak value is 1, this is 1. If this peak value is 2 from the ground, then this becomes 0.5, something like that. Okay. So select this, then this is 1. All right. So when evaluating this is the transfer function from there to here, which is 1, and from here to there is also 1. So we have 2 1s here, and then duty ratio to output transfer function is this one. Then with this setup, actually input to output frequency response is duty ratio to output transfer function. Frequency response of duty ratio to output transfer function. Okay? So this is the way of evaluating this. Okay? And this is called PWM gain or modulator gain. FM. People usually call it FM. This quantity is modulator called or PWM gain. Okay. If you use the number other than 1, then you have the scaling factor, but 1 is the best number to use. You don't have to any scaling, right? Okay, so, and this should be measured in the operational condition, okay? So, this is operating open loop operation with the fixed duty ratio. This is also operating. Converter is normally operating. This one should be measured in the operating condition of the converter. Same is true, everything is true for the measuring the frequency response of this PWM converter. In linear time invariant system, you can measure everything with the circuit is dead. Okay? You excite sinusoidal waveform without considering any bias point, but this thing has the same bias point for the measurement. So you should establish the bias condition by doing this setup. Okay, so suppose this is the hardware, then this is the diagram of measuring this. Okay, so this is the hardware. So this is the injecting the sinusoidal waveform, and this performs the frequency the duty ratio modulation, and this is our voltage. And for that, we are using this impedance analyzer. I previously introduced, okay, there are 3 terminals. This output is injecting the sinusoidal waveforms. You can adjust the magnitude and the frequency, and usually you specify the frequency band. You're not adjusting any knob, it just specify this band. Then it starts from this low frequency, 10 Hertz, 11 Hertz, it goes to 100 kilohertz gradually. Okay, that signal is generated, and here that signal is passed because of this diode. Okay, DC blocking or AC coupling capacitor, and this input voltage is connected to this. So this is input voltage sampling. Maybe this is the VS sampling. Not sampling is just okay. Sampling is different from the sampling in discrete time system. Extracting this input signal, and that signal is also going through this, passing through this, and it do the PWM with this, and generate this sinusoidally modulated switch drive signal, and this signal will generate this waveform, and output waveform has DC value, and it has some ripple component and the AC component corresponding to this frequency, and it extracts the output voltage. VS sampling and VO extraction. Okay, so this is it goes every signal is 3 different component is passing through this. Okay, because of there is a DC and the different component and the sinusoidal component, same is true here, and signal goes there, and this equipment is processing this, just getting rid of the DC component and extracting the sinusoidal component here using some FFT algorithm. You know what FFT is? Fast Fourier transform, and it generates this waveform. This is the ratio between magnitude of input signal and the magnitude of sinusoidal component AC signal. This is the magnitude curve, and below maybe phase curve will be traced out. Okay, this is the way of measuring this. This is the automatic. What I mean is, previously in the long time ago, people used this sinusoidal generator and manually sweep this frequency and get what frequency and just watch this waveform and saw this, and one dot here, one data point, another manually data point like that. Okay, if you take a look at the old paper, many data are presented in that fashion. That is the way of extracting the frequency response in the past. Now we have equipment, so everything is automatic, right? So, okay, I'll finish this up, and we will take 3-minute break. Okay, this is the equipment I was talking about. So this is a very simple story. I said impedance analyzer, but in terms of its functionality, it should be called wideband. Why wideband? Because it has low frequency sinusoidal component, it has fast high frequency switching frequency, and we are sweeping the frequency from here to there. So this amplifier gotta be very high bandwidth, all right? So maybe this will be go to megahertz range. For the audio amplifier, this cutoff frequency, you know, the frequency response of amplifier, it has mid-band gain, it rolls down, but this should have very flat gain for the wide frequency, okay? And frequency tracking, because it should track this component. So from actually there are many noise, something like that, switching noise. This waveform is crazy, okay? There are many noise, but just get rid of all the noise and just extract this component, this frequency component is called frequency tracking. It's tracking the excitation frequency through this complicated and this contaminated, corrupted waveforms. So it's called wideband frequency tracking, gain and phase is shown here. And because of this is called wideband frequency tracking, gain and phase analyzer. Okay? Understand this way. If you understand simply the impedance analyzer, you may try just measure the impedance of something, which is very absurd way of using this equipment. Okay, so we take 3-minute break here, and we'll continue what we are doing now. Okay, all right.